Thank you for coming today to our Waterloo Research Institute for Health Informatics Research. I'll get that right soon. Today, this seminar will feature John Zelek, who comes from the Department of Systems Design Engineering. So I'm not going to say too much about his seminar because Maher is going to introduce our speaker. I do have one announcement. As you know, we offer another seminar series. And our next Smarter Health seminar is on November the 22nd. It will feature Matthew Anderson, who is the CIO SIMS Partnership. He has so many titles: eHealth Lead, the Toronto Central LIN, and VP University Health Network. He will be speaking on advanced hospital systems in the context of eHealth strategies. So that will be November 22nd in room 1302 in the Davis Center. So please come and join us for that seminar. So without any further ado, Maher, will you please introduce our speaker?
Good afternoon, everyone. It is my pleasure to introduce our guest speaker today. John Zelek is a professor in the Department of System Design Engineering at the University of Waterloo. Dr. Zelek is co-director of the Intelligent Human-Machine Interface Lab. He's also the co-founder of Tactile Site, Inc. His research interests can be summarized as being in the area of intelligent mechatronic control systems that interface with human in various areas, including but not limited to wearable sensory substitution and assistive devices, probabilistic visual and tactile perception. Dr. Zelek has received several awards on his work. He's a recipient of 2004 Young Investigator Award by the Canadian Image Processing and Pattern Recognition Society for his work in robotic vision. He was also awarded a Distinguished Performance Award in 2006 by the Engineering Faculty at the University of Waterloo. Dr. Zelek's research work has been featured on various TV shows and newspapers and had interviewed in TV, radio, and newspaper. Dr. Zelek will talk today about the right information. Please welcome Dr. Zelek.
I told my wife yesterday that my talk was called The Right Information, and she got the pun, the movie, The Right Stuff, because there's a whole collection of different areas that my work falls into, and I tried to tie it all together. The research problems that I work on can be boiled down into two. One is the computer vision aspect. The other is the haptics, or touch. The first, the computer vision, is about making sense of where you, or I, or a robot is and what's outside around me. And the second problem is how to communicate, convey information through the tactile modality and also provide telepresence. The applications, assistive technology. It's interesting that a lot of my work comes from my initial work in that field, working with the CNIB. In particular, providing an assistive device or electronic technology. There are different acronyms used, which helped and assisted in wayfinding for people who are blind. And that has applications in survey and mapping, robotics, vehicles, wearable computing. Actually, in terms of survey and mapping in the robotics community, there's an acronym SLAM, S-L-A-M. It's no pun intended to WWF or anything like that. It stands for simultaneous localization and mapping. So with the camera, as you move, what's out there around me, making a map, and where am I with respect to that map that I'm creating. So it boils down to an optimization problem. And the third area, as a result of the work in haptics, stemming from the work in assistive technology, is in the area of wearable haptics. And recently, some of my students and I have become involved in providing haptics for robotic surgery. And I'll also allude to the point that it has applications in rehabilitation. So the talk structure, how I structured the talk, given that there's a whole collection of different areas, the first I wanted to talk about my work in assistive technology, in particular the wayfinding device for people that are blind. The second is the various work that our group is doing in computer vision. dealing with acquiring depth, which is implicit in the image, detection, recognition of objects, context recognition, and SLAM. The third area, the numbers to the right correspond to the number of slides. So make a mental note, so as we proceed through, you'll know how many slides I have to the end of my presentation. Wearable haptics, the fourth, is some of my work in assistive technology, assistive devices, I've applied to a third-year design course, and I think there's some relevancy, so I have a couple of slides describing that work and a couple of slides to conclude my presentation. Just to give you some statistics, the demographics in North American society worldwide, we live in a world where our average age, the population is aging. Blindness, the onset of blindness, there is a correlation with aging. Currently in the U.S., there are 11 million visually impaired people in the U.S. There's a variety of different reasons for the onset of blindness. Aging is not necessarily the direct cause, but there is a correlation. And a person who gets blindness, it affects quality of life, dignity, and independence. And it's no accident that a lot of people that are visually impaired or blind are unemployed and low income. And economics definitely factors in, wearing my engineering hat, that a lot of devices have come out that, and one of the problems is economics, that they are too expensive. Nobody's going to buy an expensive device, and it's hard to replace, in particular for the application of wayfinding, a stick that costs $30. The long white cane has been very effective for getting around, and so have guide dogs, but guide dogs are a lot more expensive than a cane if you factor in the training. Some more statistics, 180 million people worldwide are blind, have visual impairments. 40 to 45% of those are considered blind. There are different definitions. The next slide, I'll provide some of those definitions. What I found interesting is that people with visual impairments lose their lives to pedestrian accidents more frequently than their non-disabled peers, especially in urban environments. U.S., 2001, almost 5,000 pedestrians died. 78,000 were injured while crossing the street, walking to school, or waiting for a bus. The last bullet on this slide I find interesting, that cars at intersections hit 8% of visually impaired respondents. 28% reported their white canes were run over. So even though that the white cane is a symbol that the person has a visual impairment, getting to point B, going from point A, is more important to a motorist. And there are various definitions of visual impairment. I've only given one, a person with visual impairment. Then the second category is severe visual impairment, and then moderate impairment. But this gives you a flavor of how the definition is cast. It's very subjective. Visual impairment, that's assuming the person has glasses or contact lenses, and this is their vision with that device. So not able to read a newspaper, even wearing glasses, report their own vision being poor, report some trouble seeing even with glasses, and be blind in one or both eyes. And in terms of assistive technologies for people that are blind, they've been classified into 4 categories. The one that we're working on is wayfinding, or navigation would be a synonymous term. The other areas are activities of daily living, computer access, and access to graphics. It's interesting that, I don't have this on the slide, but people that are elderly that injure their hips, 20% of those have some form of visual impairment. The currently available wayfinding devices, the long cane, the guide dog, other electronic devices that have come out have used sonar or laser range finding, basically finding out how far things are away. They're time consuming. They require the person to actively scan the environment and interpret the information. Another collection of devices that use GPS, the Braille note and the tracker, have a cumbersome interface, and the economic point, they're usually relatively expensive. So in terms of the spaces that we're dealing with, these are three categories: the personal space, what I can touch; the intermediate space, what I can see; and the global frame of reference, everything around us. What we're interested in is in the intermediate space. The original goal when I started working on this, probably about the year 2000, was to replace the long cane. But it's interesting, engineers or researchers can be very myopic, and when you start interacting with people, you realize that there's this Linus syndrome from the Peanuts, that the person will not give up their long cane. It's a security blanket, and it works effectively. So as a result of performing experiments, the research evolved into actually augmenting the long cane, the existing aids. So what we're trying to do is take in visual information. So we made the conscious decision to use computer vision because blindness is about losing the sense of vision. So it only makes sense to use a camera because there's a richness of information, but there are a lot of challenges associated with it. And we also made the conscious effort of convey that information through touch. Other devices have been out there that have provided the information through the auditory channel, but actually talking to people, a lot of information is conveyed through the auditory channel. If you're standing on a street corner and you close your eyes, you can hear vehicles, you can localize in 3D. So if you decided to provide that information in the auditory channel, that comes at a cost. And that is why we chose the haptic or the tactile channel. This little video clip, the sound isn't there, so the technicians don't have to worry about the sound not coming through. It's a collection of clips of our work, clips from the Discovery Channel and CBC that were streamed together. This chap here, Jim, became blind. He was a school teacher 10 years before this video was made. This was made in 2002 or 2003. And he actually tested the device that we put together. The device in a nutshell was a stereo camera and a tactile glove. And we obtained a depth image and conveyed that depth image into tactile patterns. The tests that we actually performed, they'll be coming up in the video, were very simple. That we used pager motors that are used in cell phones. There were 3 motors that we used. On the middle finger, if that was vibrating, that meant something was in front of the person. The pinky, something to the left, and the thumb, something to the right. And this was updated 3 to 5 times a second. And the intensity of vibration inversely correlated with how far things were away. This shows some of the experiments in the lab that we set up some boxes. The volunteers, I was also told that you don't call people test subjects, you call them volunteers because they are volunteering for your work. It's important not to insult the people that are helping you out. We had them go through the obstacle course with their usual aid, and then with our device, we actually mixed up the trials and mixed up the boxes so that try to minimize them actually memorizing the course. And at one end of the room, one of my students kept repeating in a robotic voice, "I am here, I am here." So they were directed to the goal of the student enunciating a particular location. This shows the glove that we developed and a collection of vibrating motors. There are more motors than I actually described. The reason was when we prototyped the device, we tried to maximize how much information could be conveyed, and the spacing of the motors correlated with the receptive fields of our touch receptors in our hand. Okay, let me just go forward. This kind of shows the stereo camera, the left and right images, and the depth map produced. And how we translated that to a tactile pattern is we just carved up the space. How this works is that the left and the right image are correlated together. So if you had highly textured features, you would get a dense depth map. But inside environments where you have nothing to correlate, like blank walls or boxes, there are actual gaps. This is the camera that we actually used, and the glove, and we had another camera that we actually experimented with there. But this gives you a flavor of the depth map produced for the experiments that we performed in the lab. And How we compared the results, it was nice that the lab floor space was in a grid pattern, so we videotaped the results, and then we went over the video and marked it on a flat plane in a grid pattern, 2 feet by 2 feet, and compared it to something taken from path planning and robotics, that the minimal hitting path, meaning that if you started a collection of random walks in all direction, what is the probability of reaching the goal before hitting an obstacle? And assuming that a person walks with minimal hitting probability, that's what we compared our the trajectories of the people going through the experiments. There was a variety of different conditions that the people, the volunteers had, the onset of blindness, their visual acuity. It was interesting, the taking note of what adaptive equipment they have been exposed to. We were very fortunate that all the volunteers were receptive to new technology. In terms of our results, the number of subjects was low. It's hard to get a lot of subjects to come out. Not everybody wants to be involved in running experiments, especially in a laboratory environment at a university. But initial results show that the glove did perform well compared to the existing aid. The interesting feedback that we did obtain from anecdotal comments, Jim, the person that was in the video, said, "I'm taking this home. It's unbelievable. It's like an extension of my cane, like having many canes, ever neat. I don't ever want to take it off." Marty was a volunteer for a clip that we did for CBC. We had not met Marty before, and he arrived, and we're going, what's he going to say? What's he going to say? And I go, boy, we couldn't have scripted it any better. He said it felt very comfortable, not cumbersome at all, fit really well. I got some good information. So a lot of positive feedback, which is great. So I can say right now, well, we produce something, it satisfies a particular need, and that's the end of my talk. See, I get off scot-free this way. But that's not the case, because after visiting with some of the people that are blind in their homes, they wouldn't use this device in their home. They know where everything is. It's outside in urban environments. So the real world is very complicated, especially going downtown. Well, that's sped up a little bit. But avoiding people on a busy street in New York City, crossing the street through traffic, even if you know when to cross. One of the problems even crossing at a crosswalk is walking in a straight line. You saw the statistics, getting the cane run over. This is the real environment, so whatever we develop, especially if we're using as our sensing modality computer vision, it has to deal with this complexity in real time and perform quite reliably. And you cannot have hard failures. There has to be a degradation of performance. By degradation of performance, if the camera, if it's getting dark, it should do as well as the eyes. And as I mentioned, there were many experimental factors involved for the volunteers. And it's the last 4 points that I wanted to stress, that what really we have to deal with is the outdoor environment, the complexity of the outdoor environment. The other is static dynamic obstacles. The other aspect is, it's interesting that in a university laboratory, it's flat. You go outside, and even though we live in southwestern Ontario, which is relatively flat compared to Western Canada, there are gradations, there are stairs, and that's reality, detecting terrain and conveying that information. So not only obstacles, labeling, if there are people approaching. How would you like the example of going into an elevator and you were blind, and thinking that you were the only one in the elevator, the door closes, and then someone starts to talk to you? It's almost like someone materializing how you perceive it in Star Trek. It can be a very frightening experience. So knowing that there are people around you. As a side but related, one thing that we recently came up with that doesn't use computer vision but uses GPS and a compass is a belt that you feel orientation and distance. And it's kind of a platform that we hope to introduce computer vision later. But the neat thing about it is that we only use 4 motors, and we make use of the ability of the human tactile system to interpolate. So I don't even know where north is. Where is north? That way? Let's say north is that way. That way. Thank you. Audience participation. North is that way. I would feel a tingling on this side. So as I moved, I'd feel nudging. It would keep following my body. And well, that's fine and dandy, so I have a compass that I don't have to look at. But it gets interesting that we've added a GPS that it doesn't have to be magnetic north. It can be your home position. So I want to go home. It's telling me it's in that direction. And we can also convey with GPS, if we know the geographic coordinates, how far you are away from that goal location. Okay, so there are the topics that I'm talking about today kind of fall out of the assistive technology work that we're working on for a wayfinding device. The first is I want to focus on the sensing, making sense of the world, where you are and what is out there around you. And there are various projects that I want to touch upon. I noticed that when I produced my slides, I didn't have any equations. So I'm sorry to disappoint you that I don't have equations. Someone once told me academic talk is not good unless you have an equation. So maybe I should stick in the token equation. So let me get to the work that we're doing. 3 or 4 years ago, Dave Bullock, a master's student of mine, worked on visual tracking of arm limbs. The interesting aspect of his work is that it used a monocular camera and used probabilistic inferencing that we know the constraints of the human arm, what movements it can take, to home in and infer the joint angle so that we can track in 3D. And the neat part about this work, given that it's using inferencing, that it can deal with occlusion and make its best guess until it gets information. Kind of like how we perform, that if someone walked behind someone else, we can infer that person is being occluded. And the reason I've shown this work, even though it doesn't tie directly into the aspect of getting depth, it does indirectly because of this probabilistic inferencing, and there is the tracking aspects of what's going on around us, the dynamic objects. The other is face detection. There's commercial software available for doing face recognition, but one of the problems is it places a lot of constraints on where you have to be to get your picture taken. So you can do face recognition if you know there are faces in the images. So the precursor to face recognition is actually doing face detection. So once you detect the faces, then you can apply it to the recognition. And another student of mine who carried on that work, Essen Fazal, on Victor's work on face detection, actually used a different technique that, compared to the databases that are available for face recognition, his results were comparable. This shows the morphing of the image, of detecting how many local features are detected and how the face is reconstructed by the number of features that are detected. Obviously, the more detected, the more detail you get in terms of the reconstructing. It just keeps playing on and on, so you're not getting a double take. But that work in face detection and recognition, we generalize to detecting object categories. We're not talking about detecting particular objects, saying that those are people, those are cars. So actual categories, which is a very difficult problem. And this little video clip shows the ability of detecting cars and the people in real time. It shows detecting an airplane and another vehicle. So once you know what's out there, so it's assigning labels to the objects that are out there. Depth is quite interesting. Originally, we thought if you have a stereo camera, stereopsis, we see with stereopsis, we can ascertain depth. But if you take a look at the psychology of how we see depth, there are 10 different cues that we use. And binocular vision, stereopsis, is the dominant cue only in our personal space, up to 1 meter. So if you go into what's called on this graph the action space, binocular disparity is not the dominant cue anymore. So there's a lot of information coming in, and if we can make use of that, we can make sense of getting at depth information. Well, this shows again an office. Addo, one of my students' grad office, where he had the stereo camera and he kind of was rotating in his seat, I think, back and forth. And it shows again that you only get disparities where you actually have texture to correlate in the left and the right image. Another student of mine, Sam Bromley, looked at the problem that, okay, we're taking these algorithms and putting them on an embedded platform. How do we do this intelligently? We don't have to compute the depth in terms of stereopsis for the whole image frame. And what he did was use the probabilistic inferencing, a particle filter, for determining where you compute disparities. And the bottom graph it almost looks like a game from Doom, but what it shows is it's contrived data, and once you get the depth map, you can fit a plane to get at the terrain that's in front of the subject. It's a crude approach, but it works. It even gives you an indication of the slope of stairs, and the goodness of fit would tell you possibly that there are stairs there. Another student of mine, Daniel Asmar, was working on the problem of SLAM, simultaneous localization and mapping, which is a popular topic in the robotics field. And a lot of people have tackled this problem with sensors like lasers, sonar, but very few have tackled the problem with vision. And our thinking was to use landmarks, so if we could detect landmarks, making sense of the world. But first, how do you know what landmarks to use? So the precursor to his work was detecting context. So if we know the context, are we in an urban scene, in a forested area, an indoor environment? And once we know context, we can apply top-down knowledge that if we're in a forested area, let's say we use tree trunks. That turned out to be what we actually focused on in a forested area, using tree trunks to triangulate and find out where you were and what was around you. How this works in terms of context, we look at the entire video stream, in a nutshell, doing frequency analysis and looking at the patterns and using that to classify what the context is. An offshoot of that work is looking at context to define sense of place. In terms of urban planning and architecture, certain environments like downtown scenes, they say have a sense of place, whereas the outskirts of a community where you have the strip malls are placeless, are the terms that we're using. So right now, this is a side project that we're looking at. Can we use the determination of context to determine what are good buildings or what is good urban design? The SLAM, let me just put up this environment. What we did near Conrad Grebel, we acquired GIS data for the campus, so we had ground truth to compare our results. We went to Canadian Tire and bought a garden cart. It was on sale, half price, is one of those gas coupon things. It's nice how you can stretch the research dollar. Then we borrowed some equipment. We used our stereo camera. So we had a stereo camera, inertial sensor, GPS, and a computer to collect data. And Danny went out. We had a few sites here in Waterloo and the neighboring areas, but the one here is the one by Conrad Grebel. And the idea was to use tree trunks for doing SLAM, determining where you were, that being the vehicle, and where the trees were around us. We actually collaborated with a company called Planix, which was bought out by Trimble. What they have is an inertial system, expensive, that when GPS drops out, like a person walks in the building, the inertial sensors take over. Their systems cost about $250,000, and you can guess who their client is, the U.S. military. And that's basically it. And they were interested and intrigued that we can use a low-cost sensor, that being a visual sensor, to do this, and we've maintained that relationship. But they mentioned this problem of GPS dropout with tree canopies. In the survey and mapping field, they call this the tree problem. So it's interesting that we're using tree trunks to solve the tree problem. So this kind of shows the camera was moving on a pan tilt head. That's why it's oscillating between left and right. We didn't know how to set this up initially, so we overcompensated in terms of getting the data. And on the right-hand side, it shows us where we think we are and where we really are and what features we're mapping out. The results were promising. Daniel did defend his PhD a couple of months ago. So according to Danny, that was promising. The other work that we plan on continuing that work in other environments also, and I'll tie that in later on when I talk about the robotic surgery, so keep that in mind. As I mentioned, we want to get at depth. One of the problems with building the device for people that are blind using a stereo camera, the engineering, one of the problems with stereo vision is calibrating the two cameras. You can't constantly recalibrate. There's an engineering solution, but a Canadian company has developed a platform that you don't have to recalibrate. They calibrate the camera once, and it's machined very precisely that the calibration parameters are stored on EEPROM, and those are used. But in terms of the costing, that camera in mass-produced would cost about $1,000. And there's kind of a sweet spot in terms of developing an assistive device for people that are blind, that if the device costs $400 to $500 max, then it may be adopted. But if the cost gets beyond in a couple of $1,000s, it doesn't get adopted. In terms of these devices, Ontario and other provinces have a program that the person does not have to pay the full cost. If the device is certified, the government pays 75%. European governments are a lot more liberal, that they'll pay 100%. I had spoken to someone from a Dutch company that they developed a device, a PDA, that would dial phone numbers, and it was a $7,000 device. Well, they can develop expensive devices because economics is taken out of the picture. This here, what we're looking at is work that we did in optical flow. It's continued over a few years, and my student Adil is, who's in the audience, is taking that further. What we looked at, optical flow is the 3D position vectors of everything moving in the environment projected onto the two-dimensional plane. And if you compute that, you can compute time to collision, which is a derivative of depth. So we looked at a probabilistic formulation, and actually this was taken 4 years ago, my son on the swing, and classifying him. And we get clutter, because I thought he was going to kick me, and I would move the camera, then move it forward. So it wasn't a scientific experiment. It was trying to get results and integrating family life at the same time. The balancing act. The extension of that work is Adil's looking at using a particle filter with to compute optical flow for the intent of time to collision. And he's looking at spatial and temporal propagation. The results are preliminary, but compared to ground truth, the errors that we're getting are quite low, and it seems quite promising. Unfortunately, I don't have any cool video right now to show you on that. And a sidetrack, most of the work has been in the visible domain. I had this project that with the Canadian military, It's not like the U.S. military; they're cheaper. It was using the project was using infrared and getting depth from stereo using infrared. We were able to get some results that the intent was for robotic soldiers working in the nighttime. So the intent of this slide is that the work has applications in other modalities, other parts of the spectrum. So that deals with getting the information about the environment. The other aspect is conveying that information, whether on your hand or on your waist. And this introduces the part of the talk called haptics. Haptics comes from the Greek word haptikos, meaning to touch. And there's the tactile, the cutaneous sensing, that means our touch sensors, and the other is the kinesthetic. My arm is behind my back. I know the joint angle even though I'm not actually seeing it, so I'm aware of the position of my body in space. And this just gives the measurement in terms of how sensitive we are on the cutaneous is the 2-point threshold. When do two sensations blur into one? Our hands are sensitive, our head is sensitive, we're less sensitive around our midsection. It kind of makes sense. Get a friend to get two pokers and start poking you and see how sensitive you are. And there are 4 different cells, and our touch system is sensitive up to about 1 kilohertz in terms of frequency. So if we're looking at conveying information through the tactile modality, we have that range to play with. It's not linear, the response. And the different cells, if you look at the 3rd row, they've been attributed to different sensations like flutter, stretch, shear, pressure, vibration, tickle. They've been actually categorized to particular cells in our tactile reception system. And it's kind of neat that if any of you look at vision from a physiological standpoint, we do have receptors. It's almost like a foveated tactile perception where our fovea are our fingertips. That's why we read Braille. And the size of the receptive fields increases as we progress away from there. The rabbit or saltation effect, which is, I think, kind of cool, that's what I referred to before with the tactile compass belt, the ability to interpolate. If the timing was right, if you had stimulus, like 3 stimulus at 3 different points, and it was timed perfectly, what you actually perceive is something running up your arm, as opposed to 3 particular points. So it's a neat artifact of the tactile perception system. What we developed, getting back to the assistive device, this tactile glove, we didn't stimulate the fingertips. The reason was we wanted to make use of the hand that wasn't being used. The fingertips are used to read Braille. And we wanted to code the information of the environment. The utopian goal was everything that you can see, that the camera can see, conveying that through a tactile pattern. What that actually means, that mapping, that's still an area of exploration. The example I gave you was very simple. And what can we use to actually code this information? We can use intensity, patterns, location, duration of the stimulation, and other factors. And it's interesting, the reason I put up this particular graph here is that that bandwidth up to 1 kilohertz actually encompasses a lot of the musical instruments that we hear. Trivia. So what we used were pancake pager motors that are found in cell phones. And we started doing weird things with them to try to find out how much information we can convey. We took one apart. That's kind of neat. That's what this diagram is. What a pager motor is a DC motor spinning around with eccentric weight, and that causes oscillations, which causes the vibrations. In terms of the models that are out there, causes vibrations in the lateral direction and the vertical direction. Since the mounting is on the disc shape, we want to maximize those particular vibrations. So as an engineer, what we tend to do is try to develop models. Models help us understand, and they're a lot cheaper than actually building prototypes. We've developed a model for this particular motor, and we can actually predict it up to a certain amount of accuracy, how it will perform and what vibrations it produces. One of the problems with this particular design is that the intensity of vibration and the frequency of vibration are inherently correlated together. So if you could separate the two, then let's say if you can convey 3 levels of intensity and 3 levels of frequency, then you have a coding scheme for 9 pieces of information. But you can't do that. The reason I chose 3 is, I'll show you in the next slide, that we determined that we can only convey 3 pieces of information via intensity. But one thing in the lab playing with glue, what we did was we stuck 2 of these together and drove them out of mechanical phase. And we found that we can actually separate the intensity and frequency of vibration. And for short time durations, we were able to show that we can produce just DC, the force, and cancel the AC component. But then it would get back into sync, and then you flick it like this. I'm not suggesting our device would have a little hand going like this all the time, but the idea is to put a pressure sensor to mount and put a time delay to get them out of mechanical phase again. So we had various controllers that we developed. The idea, we developed this scheme for controlling these motors, all possible electrical signals that we can drive it, coded up on an FPGA, and the idea would be that you'd have a MIDI-like interface, bootstrapping on the MIDI protocol. This shows the we were looking at the bandwidth that we can actually convey through wearable haptics, and we determined it was 3 pieces of information through intensity, and it varied. We had one subject that was very adept at playing the piano, and they could actually ascertain 7 levels of information, which makes a lot of sense because they're highly trained. We're looking at other technology in terms of wearable haptics, shape memory alloys, and electroactive polymers, or they're called EAPs, because the pager motors are limited in terms of what we can convey. The nice thing about the pager motors is that they're cheap. Other experiments that we looked at was at the long cane. There's a lot of information conveyed. People had looked at the long cane to see what audio information is conveyed, but nobody looked at the position of the cane and what vibrations you were feeling at the hand. And we found that the vibration that you were feeling at your hand was highly correlated with the kinesthetic information, so there was no additional information. And because that we stacked these 2 motors together and can produce forces as opposed to vibro patterns, we started looking, well, this may have application in robotic surgery. Robotic surgery, on the left screen, I have the video of conventional surgery. You see it's very tactile. The surgeon has their hands in there and moving tissue around, whereas robotic surgery, the only feedback you get are these plier-like devices and a video feedback. So that tactile feedback has been removed. Haptic devices have been used in robotic surgery, and they're usually of the form of a robotic arm that provides you a single contact force. But what we're looking at is, well, we're not certain what exists in this particular modality, what a surgeon actually experiences. So what is the haptic experience that haptics is supposed to recreate in robotic surgery? And this is some work that we're looking at laparoscopic tools that my student Howie presented last week in Ottawa. What we did, we used Omni Phantom device to simulate the force that to control the force and the springiness, and we measured the kinesthetic information with an accelerometer and the pressure at the end gripper and at the hand gripper and tried to determine that transfer function. The interesting thing about the work that I mentioned before on SLAM, where we're looking at visual environments, what we want to look at is applying that at a different scale within the body. How it actually changes, we don't have tree trunks inside the body. Things aren't rigid, they move. but if we have a lock and we can track them, we realize where we are. Currently, what is done in robotic surgery is that additional devices are brought in and are used as position locks. And so that complicates the entire procedure. Okay. And the driving force in terms of haptics and robotic surgery is the U.S. military. This is the only one I have sound on.
Man down.
This is kind of the vision from the TATRC group, who's actually working with the University of Washington. Well, it portrays a complete robotic surgeon, but you can envision surgery in the field where the surgeon doesn't actually have to be there. And the interesting concept is also they view everything as just information, that you have a record of the entire body, a whole body scan beforehand. And this is, even though you're sensing the environment, all you're doing is exchanging information and comparing information. What's a cool video of? I told you it was a cool video. So that's kind of the vision, but it's interesting, a lot of the work in this area is actually driven in the U.S. by military involvement and their interest in making this a reality. When should I go to? 5-2 or? Okay. My whole interest of assistive technology, I've kind of adapted for a course I teach in systems design in third year, where I've made, the course has evolved into a course on product design, and the theme has been designing assistive technology for the elderly, disabled elderly. And the focus of the course is process, teamwork, communication. I make the students present to the class on a regular basis every 2 weeks. Relevancy, at every stage of the process, they have to talk to at least 2 users with that disabling condition and show them what they have. And it's okay, that's the relevancy part. Iterate many prototypes, and actually at the end they have to build something and test it on their user group. The first year, I need the mic again.
Lisa Bragg reports that's exactly what some future engineers are doing at the
This was the first year they had a little video clip.
With just a few clicks,
And some of the things they came up with. They don't necessarily all have to be high tech.
Help the second hand. Parkinson's sufferers often find it difficult to cut food. Well, now there's the electric steak knife, not available in stores yet.
It's not steak.
These University of Waterloo engineering design students were challenged to come up with a useful device to assist those who have a disability or chronic illness. This is the silver bullet.
After a lot of research and actually talking to individuals with multiple sclerosis, we found out what areas they most had trouble with in their own lives, and we decided that moving around your house is a pretty important aspect of everyday life.
Lifting a grand piano lid may be easier soon, but we can't show you the full design. Patent pending. While many of the gadgets would make life easier and more independent, many could be life-saving too. This watch helps the hearing impaired hear, set emergency alarms and sirens. And for those who tend to nod off while driving, the reality right now is there isn't much money to be made on these designs, but there is a strong future.
As the population is aging in North America in general, there will be a need for these devices that the students have come up with.
Currently, 10% of the population is over 60, and with age more likely to have a disability. By 2050, the proportion is expected to double. Lisa Bragg, CKCO.
I don't think I want a narcoleptic behind the steering wheel while I'm on the road. And this past year, one of the groups actually got their device on the front page of the KW Record. It's a walker. What they were looking at was safety in the kitchen, and they took a lift, electrical lift, and integrated with the walker. Very simple. There are devices that lower your kitchen cupboards, but they decided to put that in the walker. And this one I really liked because it was low tech. It was the elderly golfer who has back problems. So they redesigned the whole golf cart. So a lot of students want to throw computers and sensors at problems. Well, there's a place for them. And the reason I'm talking about the design phase here is that design, going through the process and identifying the needs, will identify the research problems. So they go hand in hand. So in theory, advocate real-world testing. Surgical haptics require understanding the need, which we're trying to get at. Computer vision is hard to make sense of our world. Wearable haptics, various embodiments, communications and telepresence application. Design, understanding user problems. Other applications, these vibrator motors that I didn't discuss for rehabilitation. They can cue a person, let's say if they have to go through a particular rehabilitation routine of their arm. I'm actually working with someone in Toronto that to cue them to move their arm in a particular direction. We're exploring how that can possibly be done. And this last application kind of says it all. A lot of my work stems from robotics work, but I did not have one, well, I did have that military thing, but one robot in any of my videos or pictures. But robotics are important because students like to play with robots, and they're cool. So that concludes my talk.
So we have time for some questions, and I maybe also asking each other questions, like we could pick on some of your students, like adults here and things like that. So questions, comments.
If you buy a car these days and you get a navigation system with it, basically what they're giving you is a context, the maps, and a way to find out where you are, GPS.
Right.
And I'm just wondering if you've thought of building maps into your systems. You know, right now you're doing real-time mapping in some sense.
Correct.
But you know, you could have a lot of, you know, they don't move buildings very often. You could have put a lot of static maps in there that would
yes, you could.
cut down on the amount of.
I didn't go into detail that belt idea. Well, we wanted to keep that simple, the economics, so it was more of an engineering solution. But I didn't mention that it has a Bluetooth interface. So the maps part is offloaded to a PDA or a cell phone that you can get access to the network. So it doesn't necessarily have to be on the device. There's a lot of technology out there, like in the vehicle, your navigator. The other thing that's interesting about the vehicle is that that navigator is very visual. And a driver in a vehicle is already overloaded with visual stimuli. So it's interesting if you can convey that information in another modality.
Irritating sometimes, but it talks to me.
But then you can't listen to your music. Well, there's a lot of audio information in a vehicle also.
Other questions or comments? Don't be afraid.
It is a very interesting wide range of work. My question or my comment about your work on the low vision. In the School of Optometry here at the University of Waterloo, we see a wide range of patients that are low vision and visually impaired. And we do have Graham Strong and others working in the area of low vision. I wonder if there is any collaboration or work with the people here in the School of Optometry that has been done or planning to be done.
I've talked to Graham Strong on numerous occasions about the work that we're doing with the CNIB, because what we're dealing with is no vision, right, on one end of the spectrum. I've been here at Waterloo 2 years, so it's a matter of shifting and getting acquainted and developing those connections. So I'm not adverse to it. But I know Graham, and actually the course, we had an exhibit for the design course, and he came the first time to see what we had done, and I had spoken to him on numerous occasions.
Yeah, he actually was planning to attend this meeting, but he just had another engagement that he couldn't do it today. Thanks.
Okay.
Just one quick question. I'll take it to Kathy after that. Is have you tried this with just blindfolded people, students?
Yes,
victims?
we tried it with blindfolded grad students. They did poorly. They hit every obstacle in our lab scenario. They tripped over a few times, and their results were very poor. And I don't know what you can get from that. Maybe we live in such a visual world that you don't trust the other information. It's interesting that the experiments we did perform in the lab setting, that the learning curve, when we explained how the device worked, was less than 30 seconds. And they got it. And they started navigating the obstacle course. But we gave the same to blindfolded students. And
one of the ideas would be these are kind of a worst case volunteer, because if you can make it relatively easy for them to use, then for a person who's come to depend on other senses, it might even be easier for them. So and there's sort of a worst case test of the technology. I don't know.
what grad students are the worst case?
Yeah. You.
But actually, the people that tried it that were blind, they adapted quite
Very
easily,
well, yeah.
which is interesting.
So I have a question regarding the vision part. So you mentioned that you can use landmarks to, I guess, do localization and mapping.
Correct.
And then I was just wondering, so those landmarks currently, do you have like to sort of engineer or specify things ahead of time, like you mentioned for trunks, that they were used, or is there an algorithm that just goes by itself and then figures out that trunks here would be a good feature and then automatically discovers that and uses it?
It was completely automated, the experiment, but we only tested for one environment. That the environment recognition, we only geared it for the forested area. So we knew if we were a forested area or not. And we, pre-selected that we were going to use tree trunks. So there's an algorithm for detecting tree trunks.
Okay.
And they all, I don't know, I can't differentiate tree trunks. So he actually coded in differentiating tree trunks and knowing that you're taking input at a regular frequency, so there's maximum drift, and he can differentiate the tree trunks to do the triangulation to determine where that cart was. So it was automatic.
Right, but you still had to tell, I guess, your system that tree trunks was the thing to look for, right?
Correct.
So, like...
that was a priori information that forested area, we're going to look for tree trunks.
Right.
But one can extrapolate and extend that work and automate the process of determining what to use. Is that what you're getting at?
Yeah, yeah.
To be done sometime. But it showed that it could be done. That was the proof of concept.
Yeah, I was really curious about your decision not to use the fingers in your gloves. I can understand that they are used for Braille, but it's almost like you're cutting off. I can understand, too, why you wouldn't use sound, because they need sound. It's like they're triangulating, right? So they need sound for that. But it's almost like I thought to myself, well, aren't you cutting off your research possibilities in terms of not allowing the fingertips? I'm saying that, too, because I have a blind sister-in-law, and she sees through her hands, quite literally. And so cutting that off from your system, I thought to myself, why would you do that?
In terms of getting course information, which we provided, there's something in this part of the visual field that works fine. In terms of actually getting at the detail, I think you can't get away without addressing at the fingertips, because fingertips give us the detail. You take a look at the example of the surgeon, they're only using their fingertips. But we're not there at the detail, we're just trying to get the coarse information of getting around. And the whole problem of navigating around, one of the assumptions is that we're not looking at the detail. We don't need the detail to navigate around. We can almost walk subconsciously and avoid obstacles. So the answer to your question is, if we wanted to provide the richness or try to get at the richness of what the visual stream is all about, yes, we'd have to use the fingertips. There's no other way. A group in Minnesota actually uses the tongue for conveying as opposed to the hand. And rather than having a mechanical transducer, they have electrical. So they're sending electrical current through the tongue. I have problems with that. One, electricity in the mouth. Two, it takes away communicating, having a contraption in your mouth. Yes.
Your lab trial, right? I've seen videos of the, I guess the volunteers using their can to kind of go through that obstacle.
Right.
So I'm just wondering what your child is like. Do you have one child, say, the volunteers using his can, and the second child using just the adopted technology, the camera?
Well, actually, there were three. One was using their current device, the cane.
Right.
The second was using our device. Third was using both.
Right, right.
And then we mixed up the obstacle courses to kind of take away the memory factor.
And that's the right way to do it. But in your chart, the second chart, you compare I guess the one with only can, and the second one was with the camera, right?
Correct.
Right. So I was just wondering if they're actually using both, is it more efficient, or is it they show improvement over just using one of them, or do they show no improvement? I just wonder how the two technology overlaps.
Well, I decided not to read too much into it after I discovered that doing the trials indoors has limited validity in the long run, and then we have to go outdoors, and that presents its own challenges in terms of how to evaluate how well you do. And if you're going to ask me for the answers to that, I have no clue right now. Sure, you can use GIS technology, to have the ground truth, but, how do you evaluate what is good response? Some of it will be qualitative. The idea would be to give the device to someone and let them function during their daily life in particular environments, and how well that presents the information to them.
That was a really interesting talk. And second, I have a question about our vision. We're really good at doing calculus, right? The fact that we can just catch a ball by looking at it, we can estimate the speed that it's coming at and position our hand properly. So in your research, have you looked at the problem of conveying the dynamics of how fast objects are moving and being able to avoid them?
The easy answer is no. But that is neat. No. That adds a whole nother level of complexity. But it's amazing how well we can do, especially if you get, with practice, if you play baseball, it's almost like a reflex action. I know, like throwing a football when I was in high school, like I can throw straight, but if it was between two houses, I would always hit one side or the next. Parents loved me for I did break a couple of windows. But it is amazing how well, we can do calculus or dynamics, figure out dynamics.
Is that how you ended up here, sort of the minor leagues? Is that what?
It was the fallback position.
Any other questions or comments by anyone? I don't miss anyone. The only thing I want to complain about, first of all, I really enjoyed your talk, but at the beginning of your talk, you gave us a map so that we could determine which slides. Then, unfortunately, there were no slide numbers, so I got very disappointed by that.
Well, 4 sections.
Thank you very much. I enjoyed it.
Okay, Don.